Okay, so we'll be looking at rational functions in this video. We're going to start with an example of average cost, which is one of the big applications of rational functions. There's also a lot more in physics and in the business world because so much has to do with ratios that rational functions come up all over the place. We'll look at a definition and then also what they do in the long run and short run, just as we did with polynomials. So for our example, we'll look at a brewery. And we'll say that to make a 100-gallon batch of beer can cost around $800, and each beer will sell for $5, which brings the cost down. So we can say that the cost is a function of the number of beers sold, and that would look like 800 as like our fixed initial costs, minus 5b, the number of beers, right? So as we sell more beers, that cost is going down. Hopefully we're seeing that. And we don't need this .00 here. So cost is a function of the number of beers. Now, what we'd say is that the average cost, meaning the cost per beer, well, we would take the total cost, right, and then divide by b, whatever that might be. So here, that average cost is going to be some function of b, which is f of b over b, which is 800 minus 5b all over b. So see how we're taking kind of the total cost and dividing by the number that we've sold. That's how we take averages. Same with your average test score, right? Total test score over the number of tests you take. So if this is our average cost, then we can ask, what is the average cost to make a batch if we sell 100 beers? Well, then we'd be looking at A of 100 or G of 100, and that's 800 minus 5 times 100 all over 100. So this works out to be, excuse me, 300 over 100, which is 3. So what does this 3 really mean? Well, the units are in dollars, right, per beer. So what this means is that, and I'll scoot over here, what this means is that the average cost to make this batch is $3 per beer sold, right? And we could see that if we increase, decrease, this would change the average cost per beer. So this is one application. Again, some things to note about this function in particular. Where are the zeros? And what do they mean? Well, zeros of this function, so a of b is what, 800 minus 5b over b. Anything that drives this ratio to 0 is going to come in the top. And so what we would do is set 800 minus 5b equal to 0 and solve. And so what we'll get is 800 equals 5b, so b equals 800 over 5, which is what now? 1660. Okay, so what does this mean? When 160 beers are sold, the average cost per beer is $0. So it's kind of the break-even point for the brewer to know, right? I know I need to sell at least 160 of these beers if I'm going to break even. Otherwise, each of these beers is going to cost me money, right? But again, more generally, we notice how we found the zeros. We set the top equal to 0. What is the bottom doing with this function? Well, it's driving the ratio forward as we move left to right. And when I say driving it forward, I mean driving it down, right? As we increase B, the average cost does what? It goes down, which is a good thing for the business. And again, we see this more generally in just any rational relationship. You divide by a larger number, you're getting a smaller number. So what's some things that we have to be careful of? Well, we know that B can never equal 0, right? Because we can't divide by 0. So this is important. So in general, denominator cannot equal 0. So what do we have here? We have what's called a vertical asymptote. At B equals 0. What does vertical asymptote mean? It means that the function is not defined here. All right, if you plug in B equals 0 this into your calculator, it'll be an error. It's not defined. So we have to have the fact that B is not equal to 0 as we look at the domain. So the domain of this function is really all reals except B equals 0, or, you know, since we really can't sell negative beers, it'd probably be better to say all values greater than 0 to infinity for B. And then even this infinity in the realistic context might be a little much, right? There's not infinite beers in the tank, there's only 100 gallons, so we might, you know, throw a question mark around that. But just to kind of like wet our whistle with how rational functions work, we find zeros are dictated by the top of the ratio, and the asymptotes and kind of long-run behavior are going to be dictated by the bottom. And it's a little bit more subtle than that, but we'll unpack that. So the definition of a rational function. That last one we looked at is one, and it's any function of the form p of x over q of x, where p of x and q of x are polynomials. Okay, so that can be linear functions, constant functions, and sums of power functions, so that's good. The only stipulation is q of x just can't be the 0 constant polynomial. Right? Technically, that just the function q of x equals 0 is a polynomial, but we just can't have this be the case here. So that's just kind of covering our bases. That's the definition of a rational function. So, you know, we could have an example. Any old rational function will do. This counts. We have a rational function, or a polynomial up top rather, and a polynomial down below. And again, if we were curious about what are the zeros, do we have any asymptotes? We would look to the top to find out where any zeros would be. So we'd look to see where, if ever, is this function equal to 0. And while here we could see x minus 2, x minus 1 is how this factors. And using the zero product principle, we'll see that x equals 1 or x equals 2 are both zeros for this function. So we know that when we graph this, this thing is touching down at 1 and 2. And asymptotes, what asymptotes do we have? Well, we have a vertical asymptote here at x equals 4 because x cannot equal 4. Let me put it like this. Since x minus 4 is in the denominator, and not reducible, there is a vertical asymptote at x equals 4. So what does that mean? Well, if this is 1 and this is 2 and this is 4, the function is going off to infinity here at this point. And so we're learning a little bit more about this function. And the key thing here is that it's in the denominator, but it's not reducible. If this were reducible, this would actually be something different, which we'll talk about more in a bit. So we know some of the zeros and some of the asymptotes. How about the long-run behavior? What happens when, for g of x, when x goes to infinity, or when x goes to negative infinity? Well, let's pull this over to the next page. Well, our function is x squared minus 3x plus 2, not switching it up on you, over x minus 4. So the limit of this function is going to be dictated by the ratio of the leading terms. So if leading term of p of x, so again, for it's of this form, right? P of x over q of x. If the leading term of p of x is higher degree than q of x, then the function will diverge to plus or minus infinity. Okay, so what that means is we look here and we see leading term, we see the degree of the top is 2, the degree of the bottom is 1. And so we see that the limit as x goes to infinity of x squared minus 3x plus 2 over x minus 4, as x gets really, really large, we notice that the minus 4, the plus 2, and even this term up top don't really contribute anything to the change. And we say this is really same as the limit of x squared over x, which if we simplify is the limit as x goes to infinity of x, which means this is going to diverge to infinity. Right, and if you think about it, there's more things being multiplied by itself faster in the top than it is in the bottom. So we see that that's the case there. So this is going to positive infinity as we go off into the positive tail, and then the left-hand tail here, the limit as x goes to negative infinity of g of x, well, same thing, we know this is going to be the limit as x goes to negative infinity of x. And so where is this heading? As x goes to negative infinity, where is x heading? Well, it's going to diverge to negative infinity. Okay, so we're learning a little bit more about the function. So namely, we know that it crosses the axis at 1 and at 2. We know it has an asymptote at x equals 4. And we know that at the tail, at the positive tail, it's going off to infinity. And in its negative tail, it's going off to negative infinity, something like this. So the question is, what happens here in the short run? So we'll unpack that here in a moment.